Wow, if you made it to this presentation, it means you're nearly at the end of the Year 9 section of Probability in the Australian National Curriculum. Well done. I hope you are proud of your achievements so far. So there we are. Are you proud of what you've done? We've just got to get through this last little video, and it's quite sophisticated stuff, so I think you'll like it. So let's get on with it now. And in this section, we're going to talk about compound events. Compound events. Now, books don't give much of a definition of compound events, but let's have a look at a situation, an experiment, where there is a compound event. Can you see perhaps here with this table, this lattice rather, diagram here that we did before, that there are two things happening: the results on a die and the results on a coin. So that might give you a clue as to what a compound event is. Okay, so normally in an experiment we just have one of these. Toss a coin, get a head or a tail, roll a die, get a 1 or a 6, but we don't do an experiment involving two operations, if you like, or more. You could have 2 dice and 3 coins and look at the combination of outcomes that you get from that experiment. That would be a really big compound experiment and give you a compound event. So a compound event consists of more than one thing happening, not more than one outcome. Dies have more than one outcome. The sample space for a die is 1 through 6, isn't it? Okay, so there are many outcomes for even simple experiments. But a compound experiment is where there's more than one operation happening as part of the experiment. So here we've got two things happening. A die is being rolled and a coin is being tossed. And so this lattice is a one way of working out what the sample space is. So let's go through it again now. You could have a 1 on a die and a head on the coin, or you could have a 2 on the die and a tail on the head, on the coin. Okay, so there's lots of possibilities, and this lattice is a way of counting them up and working out how many there are. So how do we work out the probability of a 5 on a die, here it is, and a head on the coin? So let's write that down. Probability of a 5 and a head. Well, you can see there that all of these are equal, have equal opportunity of occurring. So a 5 and a head, how many are there? There are, that's one possibility out of, let's add these up, should we? Add up all these dots. How many are there? I think there's 12, but we don't need to do multiple addition. We can do multiplication. For every one of the 6 results on the die, you have 2 results on the coin. So 6 times 2 is 12. We'll have 12 possible outcomes there. No need to add them up. Don't do multiple addition. Do multiplication. So this is one chance out of 12 of getting that particular outcome in this compound experiment. So our compound event, the event we're looking for, is a 5 and a head, and its probability is 1 out of 12. I wonder if we can work out an easier way of working that probability out without actually listing the sample space and counting up how many outcomes in that sample space constitute our event. Here it was only 1. All right, well, let's come on down. Here we have it. There is a quicker way. If the events are independent, that is, the occurrence of each event does not affect the occurrence of the other. And that's true about the coin and the die, isn't it? They are not connected in any way. So we're saying no matter what happens on the coin, that does not affect what happens on the die. So they are independent of each other. Independent of each other. All right, so that's a very important idea here because it helps us work out probability without listing this all out. So here's our rule, and let's go through this now. If two events A and B, so that's a die and a coin, are independent, yes they are, there's no connection between them, one doesn't affect the other, the probability of getting what? A 6 and a head is timesing the two together. Well, would that work? We said the probability of that was a probability of, what was it, a 6, and no, it was a 5, sorry, a 5, as we've got our diagram down here. The probability of a 5 and a head was equal to 1 out of 12. That was by doing this, listing the sample space on our lattice and working out one outcome out of a total of 12. This says up here, this is from Hayes and Harris publication, you should get that book. It says you times the two together. How does that work? So it's saying here, I'll just get a bit more room down here, that this would be the probability of a 5 times the probability of a head. Would that work? Let's check that out. The probability of a 5 is 1 out of 6 times probability of a head 1 out of 2. So that's 1 out of 12. Wow, that did work. Rather than counting up, here we are, rather than finding the event, the outcome which constitutes what we're looking for, which we'll call our event, is a 5 and a head, instead of finding it on there, we could have worked out the probability of a 5 independently, that is on a die, is 1 out of 6, one chance of getting a 5 on a die out of 6, and the probability of a head, one chance out of 2 on a coin, and times them. It looks like it would work. But hey, come on, we're mathematicians here. Why? You're going to ask. We're not just going to write down stuff out of a textbook. We want to ask, why does that work? Okay, so let's just put it down here. I'm going to have a look at this multiplication. So, the probability of a 5 is 1 out of 6, we agree. So it occurs 1/6 of the time. And if it occurred, it's got to be matched with a head for a coin. And that occurs half of the time. So the probability of a head is half of the time. So in other words, a half of that 1/6 of the time, you would be getting a head, wouldn't you? It's a 6, but only a half of the time, half of something is times. There we have it. A half of the time when a 5 comes up, which is 1/6 of the time, and a half of that is the chances of getting a head as well. So it's a 12th. Do you get it? The idea of this rule up here, right up the top here, this rule is really to do with the fact that only part of the time when you get your first event will you get the second one, because it's got less than one chance. So what chance has it got? It's got a half of 1/6 chance. Do you get the idea now of why that multiplication will work for us? So this is quite a breakthrough. I want you to pause the presentation, just think about it. We are replacing this approach of counting up what we want out of the total sample space from a lattice here by a rule. Only if we can say definitely that these two are separate from each other. Okay, independent. One's not going to affect the other, so we'll just times their probabilities together. Do you get it? Let's go and do a bit more with this. So here's an example. Now two spinners are alongside of each other here. Find the probability that you get a green. So here's a green on this one. And a 3. There's your 3. Now, are they independent? That's the first thing to worry about. Because we're going to try and do it with a rule, not with listing all the outcomes. Could we list the outcomes? Yeah, I think we could. Spinner 1, spinner 2. Spinner 1 is colours. Put your colours here. Spinner 2 is numbers. Put your numbers here. Yes, we could have lots of dots in there. We don't want to do that. That's very long. We're going to try and use our rule. Now, they are independent. So that's the first thing to do. There's no connection between these spinners. One doesn't affect the other. So what we've got here, one spinner does not affect the outcome from the other. So let's do them separately. What's your chance of getting a green in here? Well, it's 2 out of 5 different colours. We did this way back when. And then, when that turns up, how much of the time would you expect a 3? It would only be 1 out of 7 is a 3 here. So a 7th of the time, so a 7th of 2/5. 2/5 times 1/7. Get it? Is here 2 over 35. Remember the fractions here. 2 times 1 is 2. 5 times 7 is 35. Don't forget your multiplication of fractions. It's going to be important if we're going to use this rule. Right, get the idea? Quite nice. We don't have to, actually what we've been doing before, we don't have to do that here. We can actually ignore the total sample space, the total listing of all the possible outcomes in this compound experiment. And the compound event is a compound because it's got these 2 pieces to it. 2 things happening here. Okay, get the idea? Okay, let's just go to here. For any event E with complementary event E prime, which is an old rule now, the sum of them must come to 1, right? Because you either get E or this is not get E. So between the 2 of them, it must come to 1. You're either getting the event or not. So we said before, what's the probability of getting a 5 on a die is 1 out of 6. Therefore, the probability of not getting a 5 is 5 out of 6. All the rest are not 5s. We don't have to count them up. 1, 2, 3, 4, and 6. We don't have to do that. We can just take it away from 1 because we know if it's not a 5, it's what's left from 1. Between all of them, the total probability must be 1 because one of those must occur, must be definite. Okay, let's go and have a look then. So here we have some problems with this, using this. So Sunil has a probability of 4/5 of hitting a target, and Monique has a probability of 5/6. They both fire simultaneously, so there's no connection between these 2. What's the probability they both hit when they both miss? So let's do it with the rule. So if S is the event of Sunil hitting the target and M of Monica, then probability of both hit is probability of S hits. S is the hitting of the target by Sunil, and M. Probability of S and M occurring, both of them. So we use our rule of independence, timesing. Okay, so here, what's the probability of S? That is the Sunil getting the target. There it is up there, 4/5. And of Monica, here, 5/6. And in other words, we're going to times them together. If Sunil hits it, then 5/6 of the time, then Monica will have a chance of hitting it as well, because 5/6 of every time she hits it. So it's 5/6 of 4/5, which is 20 over 12. Or they've done some cancelling here, cancelling that, and 4 over 6 comes to 2 over 3. Just have a look at that. We might unpack that. 4/5 by 5/6. What's the best way of doing it? 5's into the bottom row here, goes once into the top. You must do the same to top and bottom in cancelling, dividing top and bottom by the same factor. And then here, 2 will go into 4 2 times or twice. 2's into 6 goes 3 times. So that's how we get this simpler answer here. You could do it 4 times 5 is 20, over 5 times 6 is 30, and then cancel top and bottom by 0. We don't do that here because it's getting bigger numbers, but you could do that. Usually we try to cancel to keep the size of the numbers down, don't we? All right, let's do this one over here. They both miss. Now, this is why they put in the idea of the complementary event. So that's the complementary event to Sunil hitting, which is S, the event S. So not S is 1/5. He hits 4 out of 5 times. So there it'll be 1 out of 5. And not M, Monica missing here, not M. So she's going to do that 1/6 of the time. So if they both miss, it's highly unlikely, pretty unlikely here. One will miss 1/5 of the time, and of those times, the other one's going to miss 1/6 of the time. So it's 1 out of 30. Do you get it? We don't have to list down all the possibilities. What would it look like if we did? We could have Sunil here, and Monica here, Monica here. I don't know why it does that. Let's just get rid of that. So M for Monica here, Monica, and Monica could hit or miss, and Sunil could hit or miss. But the trouble with our lattice here is not all points are equal, are they? Because they don't hit and miss with equal likelihood. One is 4/5 and 1/5, the other is 5/6 and 1/6. So our lattice has got a bit of a problem associated with it. So the rule will help us overcome that. Let's have a look at some problems for you. So we want to use the rule now, the rule for the probability of independent events. Okay, so we're not going to draw or list the sample space. We're not going to list it. Okay, we're going to use the rule, and the rule is the probability of A and B is equal to the probability of the two events separately and times. There it is. So you could start the rule that some books push, and that is and means times. You want both of them, both to occur. So you're going to use multiplication. And I explained before how that happens, because part of the time, part of being times, you're going to get the two coming together. All right, so pause the presentation and have a go at 15G1. I've put the answers down here because I reckon by now you are a pretty honest budding young mathematician, and you won't bother cheating the answer. You want to actually try to find the way of doing it. Please remember how to set it out. So up here we want probability of a head and a D, right? Put it out like that and then show what you're going to do, which will be timesing the two probabilities. As long as the coin and the pentagonal spinner, pentagonal 5 sides, hasn't it? Yep, there they are there, 5 sides. Okay, so we'll go back there now. Okay, 5 sides. I forgot to tick one. So 1, 2, 3, 4, 5. So just set it out so that it's explaining your answer. It's a mathematical reasoning, and that's part of the national curriculum, being able to reason and to show your reasoning for mathematics. Okay, have a go. I think you'll be good enough to go pretty well with that. Okay, so I'm going to move on now. All right, well, we talked about independent events. Can you think why events might be dependent? How would they depend upon each other? All right, I'm going to take a simple example. And again, this is from Hayes, so grab their book there. I'm going to take a box or bag of marbles here, or counters or whatever, and there are 4 red. And when we start, there's 4 red and 2 green. Okay, now if we do a draw, we could draw a red, or we could draw a green. So how do we make an event dependent? once we've taken that out, what if we don't replace it? Let's have a look at what happens here. If we now take a draw, let's do a second draw based on that. And over here, the same thing. We've taken out a green. We would be doing a second draw on this one. What do you notice? What do you notice about these second draws? Oh, they're going to be based on something different. There's only now 3 red and 2 green over here. And over here, there's still 4 red and 1 green. Can you see what's happening? That second draw is going to depend upon the first one. There's the result of the first draw, a red or a green. And if we don't put it back, look out, the second draw is going to be affected. So this is called dependent events. Dependent. What's going to happen in the second part of our experiment, this is compound, isn't it? It's a compound experiment, compound events. It's got 2 things happening, 2 draws. But this time, the second thing happening, the second draw, will be dependent on the first, if we remove the ball. Okay, if we remove the ball or the marble or the counter, remove the ball and don't replace it, then we will have a dependent event. Let's go back. We will have a dependent event. The second one will be affected by what happens in the first. It will depend upon it as to what the outcomes could be or the probability of the outcomes in the second draw. Okay, do you get it? We'll do a bit of work on that. Come down here now. So this is a bit of a silly definition, or it sounds silly. 2 or more events are dependent if they're not independent. Yeah, well, fair enough. That's what dependent and independent means in English. They either depend on each other or they don't. So dependent and independent are the 2 possibilities. Now this is the one we want. Dependent events are events for which the occurrence of one event does affect the occurrence of the other event. Okay, so the result of the first draw does affect the chances of what you're going to get in the second. Okay, it does affect the occurrence of the other event. I don't know that I like that definition. Dependent events are events for which outcomes of the first event will affect the set of outcomes of the second event, or the sample space of the second event will be affected by the first event. Okay, something like that. So fairly hard to actually explain in English terms. Okay, if A and B are dependent events, then probability of A then B is the probability of A times probability of B given that A has occurred. You've got to adjust it, don't you? I'm going to show you that in a minute. But we sometimes write this, I like PR as you know, probability of A, and instead of all these words, we often put this. You'll see this later, next year, probability A times probability of B given that A has occurred. We've already done some stuff like that. The conditional probability, given that. We've seen that before, back with Venn diagrams and stuff. It's now out of a different number, isn't it, when you're given that? Okay, so do you remember that idea of what's the probability that the student does French given that she does English? So you want where the English group, and it's out of that, not out of the total student body, because you're given that she's an English student, so that's a subset. Remember that with Venn diagrams? Might go back and check that out. All right, so let's have a look over here. This is our first scenario. So let's say, what is the probability of a green? No, let's put it this way. Hang on, I'll put a red first because I've drawn out a red. What's the probability of a red then a green in this scenario? Because we've taken it out and it's not being replaced. All right, so the red then a green here would be, right, the probability of a red was, what was it before? 4 out of 6. And now the probability of a green has to be adjusted. Now, because this one's been pulled out, it was 2 out of 6. There were 4 greens and 4 reds and 2 greens. So originally, the probability of a red was 4 out of 6, and the probability of a green was 2 out of 6. But now we've drawn out a red, so here it is here, I'll just rewrite that. Probability of a red was 4 out of 6. Now, what's probability of a green? We want red and green. Hang on, it isn't 2, 6 anymore, is it? So we have to adjust it. Hang on, let's go back. We've got to adjust it here because it's now 2 out of 5. Can you see that? This is the probability of a red times the probability of an adjusted green. Green, given that red had occurred. We are doing dependent events. We've got to put that probability in, given that. Okay, what's happening over here? What's the probability of, here we are, we've got a green, and then a red. Okay, so again, right at the beginning, we had the probability of a red was 4 out of 6, and the probability of a green was 2 out of 6. But we drew out a green, okay? So now the probability of that green times the probability of a red adjusted for giving a green in the first result. That's probability of a red given that a green has been taken. Is it necessary to adjust it? Let's have a look. The probability of a green was 2 out of 6 at the beginning. So probably pulling that out was the original situation where we had 2 out of 6. Now, what have we got? We want a red. Is it 4 out of 6? No. It has to be adjusted. Red, given that a green has occurred, because the green was not put back in. So now we've got 4 out of 5. Okay, so that's our probability. Let me just go back here. Okay, so our probability is 4/5. All right, so the whole idea is this last one. That's what the idea is about, this last one. All right, so it's fairly straightforward in a way, isn't it? Maybe the language is harder than the actual doing, because you are still using a product. You want something and something else, so you're still timesing. That idea is still true. That fraction of the time is when you'll get the combination of the two. But you have to adjust it, okay? Because you're told that something has occurred that affects what's going to happen in the second part of the experiment. Because you've got something which is dependent on what happened first. Dependent events. Okay, what happens in one affects what's going to possibly happen in the other one. Okay, so you could multiply these out here and or cancel them like that. So 4 on 15 is your chance there. And over here, can we cancel? Yeah, well, we could cancel 2's into that and 2's into that. So this would be also 4 on 15. So if we wanted to do that. But the story here is not so much the multiplication at the end, but the structure of this thing here. And that's important. All right, do you get the idea? You have to adjust for the dependence of the two events. Let's go forward now and have a look. So here's an example. A box contains 4 blue and 3 yellow buttons of the same size. 2 buttons are randomly selected, so 2 buttons without replacement. So you need to underline stuff in questions so you don't read over it. Without replacement. So as soon as you see that, you think, uh-oh, the second draw will be dependent upon what happens first. So what's the probability of both are yellow? Both are yellow. So put that down and then do this. This analysis is very, very important. Yellow and a yellow. So you're going to multiply. The first is yellow is easy. That's 3 out of 7. That's right at the beginning. The second is yellow, given that the first is yellow. I wouldn't mind you putting this, put PR too, by the way, yellow given yellow. So you have to adjust this second one because now it's not 3 out of 7 anymore. There's only 2 left, so you're making an adjustment. And there's only 2 left out of 6 to choose from. Okay, so you might look at the little picture here to help you. All right, so this adjustment is this idea of conditional probability, isn't it? There's a condition change here. Because the second event is dependent on the first, you've got to change that probability, allowing for the new conditions. So here it is 1/7, because we could actually cancel that into that, and then that into that. That's 1 out of 7. So just check your fraction work. What about the first is yellow and the second is blue? Spell it out. First yellow and bring in the word and, because it tells you you're going to multiply. Second is blue. So that's the first is yellow times the probability of second being blue. Given, don't forget to adjust. Adjust the probability because they are up here dependent. You can see you're not putting the first one back. So this is 3 out of 7. That's the standard thing at the beginning. There was 3 out of 7 yellow. But now you have, you're trying to draw a blue. So there's still 4 blues, but it's now out of 6, not 7. So an adjustment is needing to be made. Can you see that sometimes you're going to reduce both top and bottom of the fraction because the second event has removed one of the things you want. But here, you've still got 4 blues out of 6, so only the bottom one had to be adjusted here. All right, so if we try and simplify this now, 3's and 3 goes once, 3's into 6 go twice, 2's and 2 goes once, 2's into 4 go twice, so it's 2/7. Okay, do you get the idea? It's not too hard, is it, really? Well, it's common sense, because when you go to draw again, things are different, and you have to adjust. Okay, let's go on. All right, so have a go at this. Please remember your setting out. So here, the probability of part A, probability of, and we'll just get rid of that, the probability of green and green, maybe like that. Hang on, I don't like that way that does that. Green and a green. All right, so that's the probability of a green, and given that you've got a green first, so we can abbreviate it a bit, which probability of a green times the probability of a green given green, right, something like that, and fill it in. But we want a little bit of reasoning, mathematical reasoning here, not just the answers, because I've stuck the answers down here. We're not really interested in the answers. We're interested in the reasoning and the analysis from you as a budding young mathematician. All right, so pause the presentation, check it out. You might have to discuss some of these with your teacher or with classmates. I'm going to go on now. All right, now, you know that sometimes things can get fairly complex if you're, for example, doing more than one thing in your experiment. That is, if it's a compound experiment with compound events, that's more than one thing happening. Trees can help you, as lattices can too, look at what's going to happen. So here, when we start firing at the target way down here, the first part, the first two branches of the tree are one person's results here. So that's S hits, Sunil hits, or Sunil's misses. And then that could be put with a hit from Monica or a miss from Monica. And so could Sunil's miss be followed by a hit from Monica or a miss from Monica. All right, so now how do we work that out? Well, we've got to, along the tree, multiply, because we're doing ands, aren't we? Let's do the first one. Sunil hits, that's 4/5, and Monica hits. So we will say Sunil hits is 4/5, Monica hits is 5/6, 20 out of 30. We're not cancelling there. They're trying to keep it simple. Okay, so you could cancel, but they put it this way so you can see what's going on here. Or you could have Sunil hits and Monica misses. So that Sunil times Monica is that. Now here we've got independent events. We're not adjusting Monica. Would that be practical? Well, we probably have to make sure she didn't see what Sunil got first when he fired at the target, because that could affect her, couldn't it? So to keep this completely independent, with no adjustment, then you wouldn't want them to find out what the other one had done, because it might put them off or something. So it's all timesings here. So what do we realise? With a tree, you go along, you want the first thing and the second. So it's always timesing through the tree to get to the final outcome that you want. Okay, get the idea. So a tree, we're just branching back to trees to show you how to use them, not just to spot what the outcomes are or to list the sample space, but to help you use the AND rule to work out the probability of each of the possible outcomes. Okay, let's come down now and have a look at an example. So Stefano is having computer problems. His desktop computer will only boot up 90% of the time and his laptop 70% of the time. Not good. Draw a tree diagram. So okay, starting out, you've got desktop computer 0.9 of the time and 0.1 it fails. So D is the desktop boots up, and D prime or D dashed is no, it doesn't. It's a complementary event. It either works or it doesn't. Then with the laptop, the chances of booting up, they're L. So L means chance of booting up, L dash means not. So L is 0.7, L dash not is 0.3. They've got to add up to 1. It either boots up or not. So let's look at what we've done. This scenario here is desktop boots up and laptop does. This result is desktop boots up, laptop doesn't. Okay, so it's all the combos. These outcomes are all the possible combinations of what the two computers are doing. All right. And can you see, we put along the branches here, the probability. So the probability of L is always 0.7. That's the laptop booting up. And the probability of the desktop booting up is 0.9. So we're putting all possibilities together. Okay, so what's the probability that both will boot up? So that's a probability of D and L. Desktop boots up and L boots up. So that's the probability of D times the probability of L. Why? We said we want both to occur, and so we are going to multiply them. So it's 0.9 by 0.7, which is 0.63. Okay, what about the desktop boots up? Only the desktop. So what does that mean? Let's analyse it. Desktop boots up, but laptop does not. I wouldn't put that. I would put and. Desktop boots up and the laptop does not. So that's D and not L. L being a laptop booting up, so L prime or L dashed is laptop not booting up. So we will, because we've got and, we want both of them to occur, it will be timesing. So it's a probability, where is it up here? It's this situation here. So we will say it's 0.9 times 0.3, 0.27. Do you get the idea? It's not too hard. We're starting to bring together some of the other techniques we've been learning about trees and stuff to actually use them to quite quickly calculate probabilities. And you can see where this is going. Quite complex situations could be analysed with trees and with these probability rules. Okay, come on down now. Now, if two or more branches of the tree meet the description of the event, the probability for each branch is found and then they are added. So back there it could have been probability of one of them booting up. Shall we go back and have a look at that? Okay, so what's the probability that one of them boots up? So that could be only one of them. So that could be not that one, because that's both of them. So only one of them boots up, desktop and not, or not the desktop and the other one. So there were two lines there, or two branches of the tree that would satisfy. So we would say this one or this one would do. And so you could add them up. You could add up the probability of this one. Shall we do it? Well, that's 0.27. We did that. What's the probability of this one? Not desktop, so it's 0.1. This one is 0.1 times 0.7, which is, what is that? 0.07. So that's the probability of not the desktop, but the laptop does. So overall, the probability of one or the other will settle for one or the other, so we'd add them. So it would be 0.34 adding those two up. Get the idea? One or the other, we increase our chances, don't we? There are more chances out of the total, so we're going to add them up. Let's go down and just do that with this example. So here we are. We've got bag A. Oops, hang on. We've got bag A here. So let's underline it. It's got 4 red and 1 yellow. Bag B has got 2 red and 3 yellow. Okay, so underlining things helps you make sure you don't leave anything out. A bag is randomly selected, so we're saying we're not looking at the colours to be biased, by tossing a coin. So here's our compound event, isn't it? We've got two aspects. We're going to choose a bag by tossing a coin, and we're going to remove a jelly bean. What's the probability that jelly bean is yellow? Okay, so this keeps doing it, doesn't it? Here we go. So let's analyse it with a tree diagram. So here's our situation, bag A and bag E with this many jelly beans in it. So the compound event is choosing a bag and then a jelly bean. So here we are, we're starting the experiment. We're going to choose a bag. So here's the first thing we're going to do is choose a bag, and that could be bag A or bag B. Then we're going to choose a jelly bean. So that could be red or yellow after choosing bag A, or red or yellow after choosing bag B. So here we are, bag A and red, bag A and yellow, that's one of the things we want, that's why they've ticked it. Bag B and red, or bag B and yellow. So the ones we want are these two branches here, where you're going to get a yellow jelly bean, one way or the other. So let's analyse it first of all. Probability of yellow is the probability of, here's the compound event, A and yellow. You go to bag A and you get a yellow, or, I would possibly put something else in there. I'll do that in a minute. But you've got the or, you could settle for bag B and yellow. So we're going to add the probabilities. There's a line I would like you to put in here, and that's this in your analysis. Probability of yellow is the probability of A and yellow, or, I'm running out of space, or the probability of B and yellow. And then go to, so the word or instead of plus. No, perhaps I'd even like you to do this, maybe a further working line here. A and yellow, or B and yellow. Put it like that and then break it down. Probability of A times yellow plus probability of B times yellow, probability of yellow. So this sort of word analysis helps you get your thinking right. Analyze, I'll write that down, analyze the event in words first before you're going to all the numbers. Analyze the event for compound events to really pull it apart. Okay, so let's do it. Probability of A and yellow is this line here. We already said that. So here we want this happening. So it'd be probability of A times probability of a yellow. And the probability of a yellow from bag A, let's look at it here. It's 1 in 5 yellows. Okay, and bag B and yellow, what we want is this set of outcomes here, which is probability of bag B. Sorry about that. Probability of bag B is a half also. Why is it a half? Because tossing a coin gives us a half chance of this one and a half chance of this one. And then once you are in bag B, you've got 3, here they are, 3 out of 5 yellows in there. Okay, so it's times 3 out of 5. So this is 1/10 plus 3/10, which is 4/10. Doing those two fractions and adding them. Okay, so it's building up a bit because we do want to be able to analyze the event, and if it means or, as it did before, you're settling for more than one possible situation constituting your event or what you're looking for. You're just looking for a yellow, and you've got to find all the ways in which you can get it. So it's one way or the other. So you're going to add the probabilities. You're going to increase your chances. All right, let's have a look, and we'll finally get to this one here. And a few questions, answers are on the next page on this one because it didn't fit. I want you to pause the presentation and have a go now at these problems, and then I'll show you the answers. I'm going to move on. And here are our answers. So check it out very carefully because some of these trees do get a bit complicated looking, but I'm sure you'll be able to work through it. Check with your teacher and your classmates, see what you think. Okay, let's move on now. All right, here we're going to go back to the independent and dependent situation because we're going to draw some samples out of our total possible outcomes, if you like, with and without replacement. So we know if you replace it, it's not going to change the situation. We'll just keep flicking the screen now. Hang on. Here, if you replace it, it's going to be the same as at the start. If you don't replace whatever you're doing, then it's going to be dependent. It won't be the same as the start. And you've got to take account of that and adjust it. Okay, so let's have a look now. A bin contains 4 blue and 5 green marbles. A marble is selected from this bin. I take it that it's going to be at random. We really should say there, selected at random, and its colour is noted. It is then replaced. A second marble is then drawn and its colour noted. Okay, so second marble, determine probably that both marbles are blue. The first marble is blue and the second is green. There is 1 marble of each colour. Okay, so here we're replacing it. So the tree diagram will start off with the first marble being blue or green. So we have a starting point, and then each of these is, or represents, each branch here represents the outcomes of the various parts of your experiment. So in this part, there's 2 marbles. So the first marble could be blue or green. We'll do that first. Oops, hang on, just go back here. Okay, and then the second marble could be blue or green, and blue or green here to go with different results there. So you go to your first possible set of results, outcomes for that first part of the experiment, and then the second part. And you put each of these with each of these. Okay, so let's do it. What could it be? It could be a blue, then a blue then a green then a blue, a green then a green. That's the way we've got it set up there. So here we are going to look at what's the probability of a blue 4 ninths, and then what's the probability of another blue? Well, it still stays at 4 ninths. Why didn't we adjust it? Because they're independent. These events, first and second marble events, are independent because we put it back in. So what's the probability of getting a green here? 5 ninths. So a blue followed by a green. The green stays as 5 ninths because we replace the marble. They are independent. So here the blue, you want to get a green followed by a blue. The green was replaced after drawing, so there's still 4 out of 9 blues. Okay, and here, what's your probability of getting a green on the second draw? It's still the same as what it was because we replaced it. We replaced that green. So it's still 5 ninths. Right, now we're set up, ready to answer the question. Both marbles are blue. That's a blue and a blue. We would have 4 ninths times 4 ninths is 1681s. 1681. Okay, the first is blue and the second is green. I'll just get rid of that. The first is blue, second is green. Blue, then green is probably a blue times probably a green. Okay, so I will put probably a blue and green in that order. Okay, and means timesing if you like. I like the word and or to give the student an indication of whether to times. If it's and, you want both of them, you're timesing. Or means you've got more possibilities, so you've got to add up. Or is add up all the possibilities. So I might put that over here. I don't like little rules, but I want you to know how to do it. And implies you're going to times. So you're going to multiply. And or implies you're adding up more possibilities. You're getting more possibilities, so you have to add up all your chances. Okay. All right. So and we can multiply those out then. One of each colour. Or look out for that. We better go back and have a look. One of each colour. That's blue then green, or green then blue. Okay. They are 2 different colours. So you've got to put those down. B and green, blue and green, or green and blue, or they've got the word then. I like and. So you want these 2, blue and green. So here, let's have a look. This is this row here. Okay, that. So it's 4 ninths times 5 ninths. Or, so we're going to add the probability of green then blue, which is this one here. So it's 5 ninths by 4 ninths. So it's 40/81, if you like. All right, now, I don't know whether you've been thinking, I hope you have, we could have done this without this diagram, couldn't we? Think about it. We could have analysed it without the tree diagram. Both are blue, probably a blue. We could have taken it from up here. 4 out of 9. Probability of another blue, it's unchanged, so it's 4 out of 9. You didn't really need in this problem to list the tree diagram. You could have done, this is why I was pushing earlier in this presentation about this analysis. Because with a good analysis of what's been asked, and then breaking it down like that one of each colour, you've got to break it down more than that to see all the possibilities. And that's where this does help, the tree does help. But you could have sussed that out, a blue then green, or a green then blue. You could have sussed that out. So as you get better at this and your reasoning improves, you'll need less and less of the diagrammatic approach. Okay. Some of the more complicated problems always will need a diagram to suss out, maybe a Venn diagram particularly, to suss out what's going on. All right, let's go on now. Okay, so here is 15i, and I want you to pause the presentation, and the answers again are on the next page because there's a lot of them and it took too much room. Okay, so pause it and have a look, toggle ahead after you do a couple of problems, make sure you're getting them right. Oh, that's why there was as well. There's more problems there. Okay. And there are our answers to those 7 questions then. Okay, check them out. It's getting a bit more challenging now, so good luck with that. All right, our final little bit now is to go back over and look at probabilities from Venn diagrams. And Venn diagrams are very, very important ways of analysing events. Okay, so let's have a look at this. A wheel with sectors numbered 1 to 20. So circle that, underline it. Let A be the event, so here, of an odd. A is odd, and B is the event of getting a number greater than 13. Okay, represent A and B on a Venn diagram. Can you see why we would be using a Venn diagram here? Because odds and greater than 13s overlap. Okay, so let's try to analyse it with a picture. So here's our diagram here. Universal set. And then we've got odds in here, so we've got to put all the odds in this circle here. So all the odds, let's go through them, starting at 1, 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. And then over here, so that's set A, odds, and set B, greater than 13. So we've got 13. No, greater than 13, so we're going to start at 14. 15 is odd, so that overlaps. 16 is even, so that's not in the odd circle. 17 is odd. 18 is not. 19 is in there because it's odd. And 20 is there. Greater than 13, up to 20. Now, what numbers do we leave out? Well, it's all the even, so go 2, 4, 6, 8, 10 and 12. Okay. All the evens less than 13, I should have said. So this is interesting, isn't it? It really helps you analyse what the situation is. And we want probably the number spun is odd and greater than 13. So you want the intersection, it's got to be B, which has got to be bigger than 13, and it's got to be odd. So it's the ones in the intersection there. Okay, can you notice this symbol from Venn diagrams? We haven't done Venn diagrams in detail, but this means A intersection B. That means that bit in the middle. So you could actually list out all the odds and all the numbers bigger than 13 and simply look at how many overlap. So 15 and 15, without a Venn diagram I'm saying now. Here, and 17, and 17, and 19, and 19. So there's 3. You wouldn't really need a diagram, but it helps a little bit, doesn't it, to see what's going on. Particularly if you wanted to do more with this, you know, ask other questions about how many are in neither set, so that we could count up all the ones around the outside there. Okay, so our second part is our probability. So the probability of odd and greater than 13 are those 3 there. The 3 in here, if you like to take it from the Venn diagram. So it's 3 out of a total universal set, which was all 20 numbers. Okay, so just notice this symbol here now. It means intersection. Okay, so A upside down, or just N upside down U, because U means union, but A intersection with B. A intersection. So the intersection of A and B. So where they overlap or intersect. So there are 3, but different numbers there that belong in both. Well, that's where they intersect. So we could sort of shade that intersection in. All right, your turn. So here's the last exercise here. I want you to have a go at drawing Venn diagrams here. Underline stuff so that you, in your initial problem, so that you can see, if you like, all the facts that have to be put in there. Okay, so come down now. Let's have a look at some more examples. So you've got 30 students, 19 do physics, 19 are P's, 17 do chemistry, and 15 study both. Okay, display the information on a Venn diagram. Let's do that. So here's our Venn diagram. In the first case here, we've got physics, chemistry, and in the middle the overlap here. So let's have a look, and we could go straight to this one, but here we've got three numbers, A, B, C and D, to represent here. So I don't know, you might like to do it this way. We'll come back to that. I'd rather you look straight at this. So here I do this, 19 study physics. So usually you go 19 and 17 study chemistry. Hang on, I'll just do that differently. 17 study chemistry, and then 15 are in the middle, so you'd take 15 away from that and get 4, take 15 away from that and get 2, right, as you move through the problem. I think that's better than doing this. They're doing it mathematically here. A plus B has to be 19, B plus C has to be 17, and B is 15, then take them away. They're trying to show you what I've just done there, and they've got a textbook, so it's very hard to teach that, so you have to use symbols. Okay, so all of that work could have been done by the method I just gave you then, and that is, let's just do it again. So here we don't really need this if we use this method. You do physics, and you don't go to put 4 there. You start off with 19, and over here in chemistry you've got 17, and then when they tell you 15 study both, you put the 15 in, and you realise, well, 15 of the 19 are in the intersection, so here we are, you only got 4 left in that set, and 15 of the chemistry are in the intersection, so you cross that out and you've got 2 left there, right? And then overall, whatever's now, if you add this up, 4, 15, 19, 21, 9 out of the 30 don't study neither of those two subjects. Okay, so I think the crossing out method is easier to do than this thing over here at this stage. Determine the probability that a randomly selected student studies exactly one of the subjects, one of them. So one of physics and chemistry. So one means either physics or chemistry, but not both. So it's that 4 and 2 out of the total of 60, out of a total of 30 was 6/30 and 1/5, that cancels too. Given that, here we go, we did this before, given that a student does not study physics, so that's a reduced sample space now, it's not out of 30. He or she does not study physics, so it's everything outside of physics. Okay, so here's a physics set, everything outside of that. Determine the probability that the student studies chemistry. So here, they put it here, probably a student who does not study physics studies chemistry. Can we do that slightly differently? Probability of chemistry given that not physics. Do you like that? That little symbol, this is important later, means given that, so we might use that for conditional probability. Because we're given a new condition, aren't we? We're given, and there it is, given that, that's always a key word. Given that means, we're told a certain new condition. It's going to change things. So let's have a look. We're told it's out of, not physics. So we've got to go outside the physics thing. Let's get rid of all the background noise here. Okay. So here, outside of physics. So it's not in there. So what do we got? 2 and 9. So it's out of 11. Okay, so here, not given that, not physics, makes the sample space smaller. It's not out of 30 anymore. You're told some info. And how many study chemistry out of that? It's only this bundle here. So it's 2 out of 11. Do you get the idea? Venn diagrams make conditional probability quite easy because you can see that you're changing the sample space dependent upon you're given that statement. You're given a certain subset. So it's out of them now, not out of the total. Do you get it? Well, have a go at these. All right, so here are the other questions belonging to 5J. Oh, here's some red lines down here. So red in this textbook, Hayes and Harris, you want to get that, mean more difficult problems. Okay, so you might have to be very, very careful with drawing the Venn diagram here. Look at how much information there is there. You might have to underline some of that. Or write it out separately and gradually place it on your Venn diagram, adjusting the numbers according to each piece of information and reducing number in the original set by the overlap and intersection and so on. All right, have a go and I'll show you the answers. And that's the end of the presentation now. Okay, so you've made it through to the end of Year 9. I hope you've had some success. You might have to discuss some of this, but good luck with that. Cheers for now.